Hi, my name is Rene, and today we will revisit the contents of the first video with a twist. By that I mean take away two resistors, add a voltage source, and provide a trick for calculating voltages and currents in simple circuits with multiple voltage and current sources. Not to waste any more time, let's move on to the next set to see what I mean. Let's assume we have a simple circuit like this. 3 resistors and 2 voltage sources. You could tackle this problem just like we did in the first video. Write down a set of equations and solve them. Let's try. This one was quite obvious, and it's the only real node in this circuit. Now for the 2 voltage loops. We can't get any further without determining system constants. Let's say we want to calculate voltage drops and currents on all components. For that, we need to know voltage sources and resistor values. Let's say voltage 1 is 5 volts and voltage 2 set on 3.3 volts, as both are available on Red Pitaya. And let's choose all resistors to be equal to 100 ohms. With that set, we can calculate further. Expressing current 3 from the first loop, we get plugging it into equation derived from the second loop, and after tossing the equation for a minute, we finally arrive at this. Remind me again, why did I choose voltage sources and resistor values if I still ended up using variables instead of constants in the equation? Let's just insert the values in the equation and see what we get. And what are the results? Since all resistors are 100 ohms, the voltage drops on resistors are just current through a resistor times 100. And how did I do? Did I mess up anywhere? Let's check by building a circuit. To calculate the voltage drop, I will be measuring voltages on each of the 2 resistor wires and then calculating the difference. Let's take a look at the screen so I can show you how to add automatic difference calculation. So both inputs are in 10 times mode. Now let's add math functions for input 1 minus input 2, set appropriate volts per division, and add measurements for mean values of all 3 signals. I'm expecting voltage levels to be within 0.1 volt of the calculated values due to all the tolerances. Okay, let's first take a look at sources of error. Firstly, input 2 is poorly calibrated. It shows about 0.13 volts too high, but this isn't all. If I measure voltage on 5 and 3.3 volt pins, actual voltages are off by quite a bit. So I have to rerun the calculation with those numbers. But when simply entering numbers in previous equations is prone to making an error, there must be a better way. After all, I hinted at the simplification in the intro. Let's take a look. All the equations in this video had something in common. they only included addition and multiplication by a constant. Division by a constant can also be regarded as multiplication by a constant, and same goes for subtraction. Anyway, such circuits are called linear circuits, and we can solve them using superposition method. According to superposition method, you can disconnect all but one voltage or current source. Then solve the circuit. Do this for all sources and sum up the results to get the actual currents and voltages in the circuit. A word about disconnecting sources first. To disconnect a voltage source, you replace it with a short circuit. And to disconnect a current source, you replace it with an open circuit. Let's see how one would apply superposition method on this circuit. First, I will disconnect voltage 2 and solve the resulting circuit. Mind the direction in which currents are flowing, as this is very important. Moving focus to the other voltage source, we get this. Now, to add both branches of superposition and get results. I personally found this to be significantly easier than the shenanigans I had to go through before. Using this method, I also didn't make any mistakes during preparation for this video, and the results are within the margin of error from what I measured before. Even though superposition method has no limitations as to how many voltage or current sources a circuit can have, there is one limitation when it comes to complexity. This method can only be used for solving linear circuits. That meaning no inductors, capacitors or transistors. Pretty much all active components are off the table, with one exception of OpAmps. We can use OpAmps if they are used in linear operation mode. That meaning that OpAmps output does not hit saturation levels. We will look soon as to how we can use superposition to solve fancier circuits, but for today I think it's time to wrap up this video. I hope you enjoyed my equation solving skills and that you learned something useful. Please like, share and subscribe, and we'll meet again in the next video.